Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we are going to cover lecture 25 and this is part B, and we are at week 13. Today's topic is class B power amplifiers. So this is chapter 12, power amplifiers, from book Electronic Devices and Circuit Theory. This is a class B amplifier circuit, and it is implemented with two transistors. One is NPN and other is PNP. So each transistor conducts for only one half cycle, that is for positive half cycle. In this duration, NPN transistor would be on, and you will get output for one half cycle. And when for the negative half cycle, the PNP transistor would be conducting, and this would be off, and you will get the negative half cycle through this transistor. So this cycle is produced at the output when NPN transistor is on, and this is produced at the output when PNP transistor is on. So this circuit would work in a push-pull configuration. So it is also called class B push-pull amplifier. These two transistors would require to reproduce the input signal at the output. So you can see that for class B amplifier, you are not biasing the transistor, DC biasing the transistor at the load line. So operating point would be at cutoff, that is when input signal is 0, then the base current would be 0, and there would not be any collector current, and no power would be drawn from the battery. This would also be in the off state when input is 0, and there would not be any current drawn from this battery as well. So there are two voltage sources required to implement this push-pull class B amplifier. Later on we will see we can use only one source and connect this terminal to ground as well, but for that we required capacitor at the input and output side of the circuit. So with these two power supplies connected, and with these two transistors, this is the load across which the output is being delivered. So for an input voltage of a sine wave, you will get a sine wave at the output. The level of these two voltages would be equal, because still it is common collector amplifier. Input is at base and output is from ammeter for each transistor. So the voltage gain of this amplifier would also be unity. So input would be equal to output. So input is Vp sin omega t, V out is also Vp sin omega t. This peak value would be equal to this peak value. So there is a slight attenuation in the output signal, because 0.7 volts would be drop across base emitter junction. So this voltage peak value would be 0.7 less than this peak value. So for small amplitudes of input signal compared to 0.7 volts, crossover distortion will be significant. So in this output there would be a crossover distortion. Now as you can see that when input is 0, output would also be 0, because when input is 0, base current is 0, and collector current would be 0, and emitter current would also be 0 as well. So when emitter current is 0, then there would not be any current in the load, so output would also be 0. When you increase the input from 0 to 0.7 volts, this junction would not be forward biased until 0.7, so current would remain 0 and output would also remain at 0. So when output is 0, between 0 and zero point 0.7 volts, then then for this input signal between 0 and 0.7 volts, output would remain at 0. So this thing is called crossover distortion, because when input is between 0 and zero point 0.7 volts for positive side, and for negative side it is increasing from 0 to minus -0.7 volts, this transistor would be off. So for a band of 1.4 volts, there would not be any output voltage. The output voltage would remain at 0. So this would the signal would be distorted, that is, you will not get pure sine wave at the output. So this distortion is called crossover distortion. However, for large signals, if this signal is of the order of tens of volts, this 0.7 volt distortion would not be more significant, and we can ignore the distortion if we can ignore the 0.7 volts in the output. So V peak would be approximately equal to the input peak would also be approximately equal to the output peak. Now with the output voltage defined by this relationship, we can find out the output power, and that output power is equal to V square over RL, and converting into the RMS value, we will get output power equal to Vp square over 2RL. So for maximum output power, this peak value should be maximum, and the maximum value we can get at this for this circuit is VCC. So P out max would be equal to VCC square over 2RL. On one side it would be at VCC, and on other side it would be at minus VCC. So peak to peak value would be equal to 2 VCC, and peak value would be equal to VCC. Next is the input power, and then we will find the efficiency. So input power is taken from the VCC supply. So there are two batteries connected, one is plus VCC and the other one is minus VCC. So we have to multiply this power by 2 to get the total power drawn from the both voltage sources. So let me find out what is the power drawn from one voltage source. The current drawn from any source is given by the half of the cycle of the input signal. That is, we have seen that only one transistor would be conducting at one time. So for half cycle this would conduct, and a current would flow from this battery, and for the negative half cycle this would turn on and this would turn off. So when this would be off, there would not be any current from this source. So current would have zero value for the negative half cycle, only current would flow for the positive half cycle. So you will get a collector current or current from the positive supply as ICC, and it would have a half wave signal, and its average value would be given by peak value divided by pi, and so the peak value I peak would be equal to V peak divided by RL. So this peak value would be equal to voltage peak value of the voltage divided by the load. So this is the peak value of the voltage Vp divided by the load resistance. This current would be the peak current, and this current would be equal to this current, as when this transistor is on, this would be off, and then this current would flow through this path through the load, as no current would be flowing in this path during the positive half cycle. So once we have the average value of the current, we can plug the value here. We will get power would be equal to VCC into this, and then multiply by 2 to calculate the power drawn for both sources. So this power is drawn from one source, and multiplying it 2, we will get power drawn from both sources. Then we can compute the efficiency. Efficiency is the output power over input power. Output power is related with this expression, and this is the input power. So we will get, after simplification, this expression which is pi by 4 Vp by Vcc. So for maximum efficiency, this Vp would be equal to Vcc. So Vcc divided by Vcc, this would be cancelled, and we will get pi by 4, which is 0.78, and in percentage it would be 78%. Next is power dissipated by the transistor. So power dissipated by the transistor would be equal to power dissipation would be input power minus the output power, which is the power dissipated in both transistors. So by plugging the values of input power and the output power, we get this equation. Now when this power would be maximum, that is power dissipation would be maximum when we get for maximum power dissipation in the transistors, the derivative of this power for against the voltage value of the output signal, that is partial PD by partial Vp, should be equal to 0. So at maximum this slope would be 0. So differentiating this expression with respect to the voltage Vp, we will get this equation, and equating it to 0, then we can find out the peak value of the output voltage from this relationship as 0.66 Vcc. Then we plug the value of Vcc, plug the value of Vp in the original equation of power dissipation. Then we can find out the maximum power dissipation as Vp max, PD max would be equal to this expression, which is 2 by pi square Vcc square over RL. So this is the power dissipation by one transistor. This was the power dissipation in both transistors. So divide it by 2. So half of the power dissipation would be occurring across NPN, and half would be across PNP. So power dissipation in one transistor would be 1 by pi square Vc square by RL, or if we multiply it and divide it by 2, we will get 2 by pi square Vcc square by 2RL, and this is the maximum power dissipation. And power dissipation in one transistor would be equal to 1 by 5 of approximately 1 by 5 of maximum power dissipation, because 2 by pi square is roughly around 1 by 5. So let maximum power output power is 10 watts, then the maximum power dissipation is 10 watts, then the power dissipation in one transistor would be equal to 10 by 5, which is 2 watts. So compare it with the earlier case of class A power amplifier, in which a 20 watts transistor was required to deliver the same 10 watts to the load. So in this case, if I am delivering the output power from class B amplifier, 10 watts power delivering from class B amplifier, maximum power, then the power dissipation in transistor would be 10 by 5 only 2 watts. So as compared to the 20 watts power dissipation in class A amplifier that we have covered in the last previous class. So let me take an example of class B amplifier in which you are asked to design a class B power amplifier to deliver 10 watt output into a 10 ohm load. So this is the same specification that we have designed for class A amplifier. Now we are designing class B amplifier with the same specifications. So we want to deliver 10 watts here to a 10 ohm load and using a class B amplifier. So it is using 2 power supplies and 2 transistors and a load. So we know that output power is given by this expression, from which we can find out the value of VCC at P0 and RL are given. So VCC would be equal to 14 volts. So the value of these 2 power supplies would be 14 volts. This would be plus 14, this would be minus 14. So the only thing now need to specify is the transistor ratings. So for that we need to specify both transistors. Their rating are power dissipation, maximum power dissipation, and the current and voltage rating. So the current voltage rating should be such that VCE max across any transistor should be greater than 28 volts, and IC max, the current that would flow, maximum current that would flow in any transistor's collector should be greater than VCC by RL, and VCC is 14, RL is 10, 1.4 amperes, and the power dissipation, maximum power dissipation relationship that we have derived just now is 2 by pi square P naught max, which is 1 by 5 P naught max, and it would be 2 watts. So power dissipation for maximum power dissipation for each transistor should be greater than 2 watts. So maximum power dissipation rating should be greater than 2 watts. That is the transistor which we select to use in this circuit should be of power rating greater than 2 watts. So this is about class B amplifier. There is a variety of class B amplifier circuits. One of the possibility to implement class B amplifier is that you use both transistors of the same type, that is both are NPN, and other possibility is that you use complementary symmetry circuits, that is one is NPN and other is PNP. That is, you can see here, one is NPN, other one is PNP. So the idea is that one transistor should be conducting for one half cycle. So if you use both NPN transistors in a circuit, then you have to generate the input signal in a complementary fashion. That is, these two signals should be out of phase by 180 degree, and when you use complementary symmetry transistor, then then you do not require any complementary signals at the input. You just feed the input signal as is to the input circuit. But if you have both transistors of the same type, that is both are NPN, then you have to generate the complementary signals to operate the two transistors, one transistor at a time. So one of the method is use the center tap transformer, in which you apply input signal, then this then at the secondary of the transformer you will get two signals which would be out of phase by 180 degree. Or you can use the transistor to split these signals. If you feed this input, then at the collector and emitter you get two out of phase signals. or you can use the inverting amplifiers like this. This is the amplifier which inverts the signal, and then one signal would be inverted and the other one would pass as it is from the emitter follower circuit. So these are the phase splitter circuits. So this is the implementation of push-pull amplifier with both transistors, NPN, and a transformer. Center tap transformer is used to generate the out of phase signals. This is the complementary symmetry circuit, in which these two power supplies are used and output is taken from the load. There is another type called quasi-complementary circuit, in which this is playing the role of NPN and this is playing the role of PNP transistor. And these are the Darlington transistors. This is the complementary symmetry push-pull circuit using Darlington transistor. This one is using the feedback pair. One is the Darlington pair and another one is the feedback pair. So that's it for today's class and from the class B amplifier, and this would be the last class for this course and this semester. Thanks a lot. Allah Hafiz.